Okay, so most of you are familiar with radians and how we measure that, but just as a quick review here, if we have something that's going in circular motion and we have it covering a certain angle, that's supposed to be straight, okay, this is the radius, okay, and this right here is going to be an arc length. This is going to be the distance traveled from here to here. And that is going to be in meters. And the radius is going to be in meters. And theta is going to be the angle measured in radians. And so we have S in meters, we have R in meters. And so radians is really kind of not a real unit kind of thing. It sort of appears when we want it to be and disappears when we don't need it. It's sort of like the room of requirement in Harry Potter. And so we have this relationship here that we know what degrees are, and 180 degrees is going to be pi radians. So if we ever need to convert, we just need to use that. The other thing that we could talk about are revolutions. And so one complete revolution meaning 2 pi radians, 360 degrees, and just use those to convert when the problem requires it. All right, I need to show this to you in class because it's kind of something that we have to do together. I can't really show it here, but let's just suffice it to say right now, if a point is going to rotate counterclockwise like so, we're going to give it a positive arc length, a positive S, and if it rotates clockwise, so let's try it like, oops, I meant to do that in a different color, come on, green. If it rotates clockwise, okay, we're going to give a negative, all right, and we'll look at a way to maybe remember that, but that's what it's going to happen. So just kind of keep a lookout of how something rotates, clockwise or counterclockwise. All right, so we're going to start out with some pretty easy problems here. It says we've got a child on a carousel rotating clockwise, so we know we're going to have a negative arc length, and they're going to travel 11.5 meters. So our S is going to be 11.5 meters. It has a diameter of 8 meters, so we have a radius of 4. And it says, what angular displacement does the child travel? And so we simply will take our theta, our angle, to get it in radians. We're going to go 11.5 meters over 4 meters, and we're going to get an angular displacement of negative 2.88 radians. A made-up unit. Now, let's look at the wording here, displacement. If we were doing this linear motion, it would be an x or a y. But because it's angular displacement, it's theta. So we need to really start looking at the counterparts to linear and then look at their counterpart in angular. All right. If you ever wanted to find out how many revolutions that is, you just have to remember that 2 pi radians is 360, well, if you want to go to degrees, you could do that. Or if you wanted to go to revolution, just put 1 revolution there. Okay. All right, let's look at another angular quantity. Now, what we would do in linear is the linear part of this. If it was linear, we would say the velocity is going to be meters per second, the linear distance over time, and it would be v. This time it's going to be the Greek letter omega, and a lot of people just call it w, but it's omega, and we're going to take the angular displacement, not the linear displacement, but the angular displacement in radians over time. So radians per second. And again, we're going to do kinematics again, but this time with the kinematics, we're going to make sure it's all angular stuff. So radians per second, and if it's revolutions or degrees per second, just change it so it's radians per second. So thinking about the difference between angular speed and linear speed, if you've ever done the, I forget what it's called, but you whip the person around in a line, and the person at the very end is going to be way out here in this circular motion. And so if this line is to stay together, what's happening to the people along here? And this is going to be really important to understanding this stuff. This person is not going to travel a very far linear distance. This person's going to go a little bit further linear distance, this person even further. So if you're talking meters, the person at the very end is going to do the greatest linear speed. This poor person right here is going to have to go really fast, linearly, compared to this person. But they all are covering the same arc, not arc length, they're all doing different arc lengths, but they're all covering the same amount of radians of angular displacement. So they would all have the same angular speed, but they would have different linear speeds, because you can see them covering more meters per second, but they're all covering the same angular speed. Okay, so again, keeping it pretty easy here, we're going to have a kid spinning clockwise or counterclockwise, and because it's counterclockwise, we're going to have, it's going to be positive arc length. And, okay, they travel a theta of 10 pi radians, and they do that in a 10-second interval. Now, I am not speeding up yet. We're just simply getting to this whole idea of angular stuff. And so we're looking at an angular speed of pi radians per second, positive. Okay. Now, what if we want to speed up? Well, if we want to speed up linearly, what we do to speed up is we go acceleration is equal to v sub f minus v sub naught over time. We're so used to that by now. But now what we're going to do is the Greek letter alpha. Sometimes people just call it fishy, but it's Greek letter alpha. And it's going to be the final angular speed, omega, minus the initial angular speed over time. So, I don't know if that's going to, okay, I'm going to squish it all in here because I'm not sure that's going to work. I'm going to find the angular speed here by taking the final minus the initial over time. So the final angular speed is 28 radians per second. The initial was 21.5 radians per second. And that is the circular speed up done in 3.5 seconds. So we're going to go ahead and get 1.86. The units are going to be radians per second squared. For linear, of course, it's meters per second squared, but for angular, little alpha here, 1.86 radians per second squared. Okay, so this probably leads us into the next thing you're probably expecting, and that is, yes, angular kinematics. So if we look at the linear counterparts, it was x is equal to v sub naught t plus 1/2 at squared. V sub f was equal to v sub naught plus at. X or y was equal to 1/2 times v sub naught plus v sub f times time. And v sub f squared was equal to v sub naught squared plus 2ax or 2ay. Okay? And in this, the only thing you want to remember is once you have this angular displacement, you want to realize that that is arc length, distance traveled around, like so, over radius. So just be careful if they ask you for the arc length, that's going to be in meters, or if they ask you for angular displacement, that's going to be radians per second. I mean, just radians, sorry. The arc length in meters, radius in meters, they cancel and give you radians. Okay. So we'll just do a quick problem here. We have a circumference of 43 meters, and so we're going to travel 160 meters around the tree. So the arc length here is 160 meters. I can set this equal to 2 pi r and solve for r, 6.84. I would encourage you to check that out, because if you, by the way, if you take 43 divided by 2 pi and you don't divide by 2 pi in brackets, it actually does it wrong. It multiplies by 2 or divides by 2 and multiplies by pi or something crazy like that. So just check that out. So if I want to know the angular displacement, I'm going to take 160 over 6.84 and I'm going to get 23.4 radians. Okay, so that's theta. That's like your x or y if you're doing this linearly. It accelerates, so we're speeding up. Now, if you remember last chapter, we just had a constant, nice angular, constant angular speed. But this chapter, we're going to speed things up. And we have our initial is 0, and we're wondering what our final is. And so if you look at all of them, the only one that is going to be useful to us is this one. Come on. And we end up with 1.53 radians per second. Okay. So we're kind of going back to same old, same old. All right. Let's just do one more before the video ends. We have a constant. So this is our alpha. We have a circumference of 7 meters. So that doesn't really tell us how many times we're going around. So we're going to set that equal to 2 pi r. And so our radius is going to be at 1.114 meters. If the particle starts with this angular speed and it gets tripled, so our final is going to be triple. Okay, what is the distance the particle travels? All right, so the first thing I'm going to do is I'm going to solve for theta because I need to know what the angular displacement is to find meters or distance. Okay, so again, if you plug this into this formula here, we are going to, well, plug everything in. Plug W sub f in here, W sub naught, plug in here, theta, go ahead and plug in there, and let's solve for this. So theta turns out to be 0.576 radians. Now, we know that theta is equal to S over R, and we solved for R up there, and R is going to be 1.114 meters, and so S turns out to be 0.64 meters. Okay, so we don't really go very far around it. All right, that's about it, and then we'll go to the next video.